Hi, my name is Sagar. In this presentation, I'll be talking about our work on translating natural language instructions to computer programs for robot manipulation. For many complex tasks, it can be difficult to write a program to control the robot. It is often easier to teleoperate the robot using some sort of input device like a VR controller or a joystick, and to show how to perform the task. Imitation learning aims to use these expert demonstrations to train a neural network to control the robot. But teleoperated demonstrations are not the only way. For many tasks, such as following instructions in natural language, expert programmers can concisely specify how to perform the task by writing a program to control the robot. Rather than directly controlling the actuators of the robot, we propose translating the natural language instruction to a program code that can control the robot and accomplish the specified task. This is what our overall system architecture looks like. The camera feed captures the scene and is processed by an object detector to get the positions and sizes of all the objects in the scene. The natural language instruction is translated to a Python function. The objects in the scene are passed as arguments to the generated function, which controls the robot using its API. Here's an example. We have two objects, a lock and a magnet, on a table. An overhead camera captures the top view of the table. The image captured by the overhead camera is passed through an object detector, which we see has detected two objects, a lock and a magnet. The instruction, topple the lock in this case, is passed through the neural translation model, which predicts the tokens of the Python function body. We construct the Python function and then pass the objects that we received from the object detectors as arguments to it. When executed, this function uses the API of the robot to control the end effector of the robot to accomplish these tasks specified in the natural language instruction. Here are a few more examples. This one is a compound task in the test set, which is a combination of two simple tasks that resembled ones that were in the training set. Notice that we're picking up the box and then we're using it to push the bottle off the edge of the table. If the bottle is present at the opposite edge of the table, we notice that it is still successful in pushing it off. Here's a failure case where the object detector has not localized the object with sufficient accuracy, and because of that, the robot is unable to pick up the cap. This is our neural machine translation architecture. The tokens of the natural language instruction are passed through a pre-trained BERT model, which produces a vector corresponding to each token of the input instruction. These vectors are passed through an encoder by LSTM, which is followed by a decoder LSTM, which at every time step predicts a token of the Python function body. Once we have all of the tokens of the Python function body, we simply concatenate them to construct the Python function. So why translate from natural language to code rather than directly controlling the actuators of the robot? What are the advantages of program synthesis? One advantage is that the generated program can access modules like, say, NumPy or a constraint solver rather than training a neural network to clone the behavior of the module. Consider this example. Place the apple at the left top corner, the orange at the right top corner, and the banana at the bottom edge so that it is just to the left of the orange. Now, one way is to take this instruction and then pass it through some neural network that directly predicts the position of all of the objects. Alternatively, we can predict the inputs to a constraint solver. We can have the neural network predict the inputs to a constraint solver and then have the constraint solver come up with the positions for us. We find that this way of utilizing various modules to compute the answer for us gives better results. Another advantage is that the program representation is often richer and carries more information than teleoperated expert demonstrations. For example, consider this instruction: push the bottle off the edge of the table. The program written by the expert for this instruction would consider the different positions of the bottle. And the program considers all sorts of edge cases, like what if the bottle is close to the right edge or close to the left edge or the top edge, and so on. Whereas a single expert demonstration would tell us only about what to do when the bottle is in a particular position relative to the edges of the table. We would need many more teleoperated demonstrations before the network can learn to figure out what to do or what are the different edge cases and what to do about them. Another advantage of program synthesis is that the generated program is interpretable, unlike a policy network that directly controls the actuators of the robot, which is more of a black box. So to evaluate this program synthesis approach, we defined two tasks. One is the arrange task and the other is the manipulation task. For the arrange task, there are a bunch of objects on the table and they have to be arranged as specified in the natural language instruction. And for the manipulation tasks, the objects on the table have to be manipulated as specified. So here's an example from the arrange task. Place the lemon at the center, the apple just below it and to the left of the lemon, and then the banana above the apple and on the top edge, and the banana to the orange to the right of the banana and just below it. Notice here that the generated function is invoking a constraint solver and defining a bunch of constraints, and the constraint solver looks at these constraints and then predicts the positions of all of the objects. Note that the code to actually move the objects is not generated, since it is common to all the samples in the arrange task. Here we're using the Cassowary constraint solver, which underneath uses the simplex method, and we specify constraints rather than directly predicting the object positions. So here's an example from the manipulation task, and the instruction is to topple the bottle over the edge of the table. Notice that the program considers different positions of the bottle depending on the position of the bottle, whether it's close to the right edge of the table or to the left edge of the table and so on. The end effector movement that it generates is quite different, and it accounts for all of these different bottle positions. So here's another example from the manipulation task. Here the instruction is push the strawberry towards the orange. Notice that the generated program is using the trigonometric functions from the math module in the Python standard library. Whereas if we were to do direct neural actuator control, the network itself would have to implicitly compute all of this to predict the trajectory. To evaluate our program synthesis approach, we collected a parallel corpus where for each natural language instruction, we have an expert write out the program to control the robot and accomplish the specified instruction. And we also had an expert teleoperate the robot to accomplish the specified instruction. So the arranged dataset has a parallel corpus with about 100 training examples and 11 test samples. The manipulation dataset likewise has 122 training samples and 12 test samples. The baselines are policy networks that directly predict the actuator command. For the arrange task, an LSTM processes the tokens of the input instruction, and it's followed by several fully connected layers. At the end of that, we get the positions of all of the objects, which are taken by a separate routine and to control the robot to move the objects to the position specified by the model here. For the manipulation task, the input instruction is passed through an LSTM like before, and then at every time step of the decoder LSTM, the decoder directly predicts the end effector position and the gripper state at every time step. Traditional NLP metrics like the BLEU score are not suitable for code generation because a very slight error like changing a plus to a minus in an expression can cause failure in performing the task. Likewise, it's possible for the generated program to be very different from the expert program and yet accomplish the task and might even have the same trajectory as the expert program as well. Because of this, we don't use something like the BLEU score, and we use an extrinsic metric, which is the accuracy. What we do is that for any given natural language instruction, we generate the program and then execute the generated program and record the trajectory of the end effector of the robot. And then subsequently for the same instruction, we also execute the expert program and record the trajectory as well. If the recorded trajectory of the predicted program and the expert program are within 10% of each other, then we consider that to be a success. The syntax error rate for the arranged dataset was 0.6%. These are cases where the neural machine translation model generated a program that had syntax errors in it. And for the manipulation dataset, the error rate was 2.81%. Now for the overall results where we compare the expert and generated trajectories, the baseline models which are directly operating on the actuators of the robot perform much worse. And this is because we have only about 100 examples and the natural language instruction following task is a rather difficult one. Whereas even with these few examples, our proposed machine translation model is able to achieve much higher accuracies. Here's a sample program where the instruction is pick up the strawberry and drop it past the bottom edge of the table. Notice that when it's generating the movement of where to move the strawberry to, it is looking at the attention is focused on the bottom edge of the table, which is what we would expect. We found that it generalizes well to synonyms of words, and if we construct compound tasks from simple tasks in the training dataset, then the generated program behaves the way that you would expect it to. Here is a sample incorrect prediction. What we generally noticed is that when there are too many phrases in the input instruction, the generated program tends to be incorrect. And what seems to be happening is overfitting, because there are very few training examples which are very long. So once we get a long natural language instruction, the generated program as well, whatever was in the training set. So it's not really looking at the input instruction at all, and simply based on the length of the input instruction, it seems to be predicting one of the training set programs. So generally for these long instructions or instructions with many phrases, our system performed very poorly. So to conclude, computer programs are a precise way to specify tasks and can offer a richer representation of the intention of the expert. The generated programs can outperform direct neural actuator control, and the generated programs are more interpretable than policy networks that directly predict the actuator command. I would like to thank the Robert Bosch Center for Cyber-Physical Systems for funding support and to NVIDIA for providing the GPU used in this work. Thank you.